Okay, here we go with part 2. And in this part we're going to look at some expected features of the system whose equation we came up with in the last part of our fantastic HBO original here. And so in the last time we ended with the equation of motion. We ended with the equation of motion of the damped driven pendulum. So we ended with phi double dot plus 2 beta phi dot plus omega naught squared sine phi equals gamma omega naught squared cos omega t. And now we're going to look at how the system behaves when both the driving force, so gamma, is very, very small, and if the driving force is going to be small, then our displacements are going to be very, very small. And we're going to assume that it's released from rest, so our gamma initial or phi initial is going to be equal to 0. And so since the displacements are so small, we can make the standard assumption we make when we're working with pendulums is that phi is going to be equal to sine phi for tiny displacements. And so this is going to be basically a simple harmonic motion equation. So we're going to end up with phi double dot plus 2 beta phi dot plus omega naught squared phi equals gamma omega naught squared cos omega naught. And so we've already kind of looked at solutions to this equation, and we know that eventually once the transient effects have died out, this whole system is going to oscillate with the amplitude and frequency of the driving force. So this is our solution to our equation. And if we plot this, we can plot this for, let's say, lambda is very small, so less than 0.3. And we'll let the drive frequency be equal to 2 pi. And so the... what am I doing? So the period of the system is equal to pi over the drive frequency, which is just going to be equal to 1. So every period is going to be equal to a period of our drive frequency. And so if we graph this motion, it should be tau, and tau is going to be equal to 1. We're going to have phi here, we're going to have time going along here. And this is going to be broken up into units of the drive period. And so say we have 0.3, sorry, I don't know why that's negative. Get rid of that. Negative 0.3. And we're letting this go from rest. And so I'm going to add some more periods here, just so we can get a few more, see a bit more what's happening. So we let it go from rest, and there's a brief transitory phase before it eventually settles down to simple harmonic motion with the amplitude and period of the driving force, which is what we'd expect for a damped driven oscillator. And sorry, not quite the amplitude, but with the frequency of the oscillator. And that's not unexpected at all. So what we do see is that after the transitory effects, the motion gravitates towards this attractor of the driving frequency. And one important thing to note is that linear systems like this only have one attractor, so there's only one possible stable state that they gravitate towards as time goes on. And we know from studying these systems that this system will continue to oscillate like this into infinity forever. And yeah, that's nothing new. We've studied those before. And so now we can look at near linear oscillations, near linear features of the damped driven pendulum. So in this case, theta or phi is still going to be small, but it's not going to be tiny. And our gamma is going to be small, but it's not going to be tiny. It's still going to be less than 1 though, so it's still a small driving force. And so in this case, we'll make a different approximation. Sine phi will not be exactly equal to phi, but it'll be pretty close. And so we can use a Taylor approximation. And the Taylor expansion of sine phi is equal to phi minus 1/6 phi cubed. And now we can sub this back in to our equation of motion. And we get phi double dot plus 2 beta phi dot plus omega naught squared phi minus 1/6 phi cubed equals gamma omega naught squared cos omega t. Alright, and since this term here is going to be very, very small because both these terms are going to be small because our phi's are very small and our gamma is still pretty small, we can still approximately say that our solution is going to be basically the same as it was before. So it's going to eventually oscillate with the frequency of the driving force in some approximation of its amplitude, or at least its amplitude will be in some way related to the amplitude of the driving force. Omega t minus squiggly man. Okay, and so if we sub this into here, we're going to see right away that we're going to end up with a cos cubed term in the left side of this expression, and we can use identities to show that this cos cubed term, cubed of omega t minus squiggly man, is going to give us 1/4 cos 3 onto omega t minus squiggly man plus 3 cos omega t minus squiggly man. And so we're going to end up with a term on the left side of this equation that has a factor of 3 multiplying the drive frequency. And we can see on the right side that there is no term that has a factor of 3 multiplying the drive frequency. So to end up with this, to have this equation balanced by the solution, we're going to have to introduce a multiple of 3 of the drive frequency back into the left side of this equation. So we can refine our solution a little bit further. It's not exact, but it's a better approximation by saying that phi of t is going to be roughly equal to a cos omega t minus squiggly man plus b cos omega t minus squiggly man, where in this case b is going to be a lot smaller than a. It's going to be larger than b. So this lets us, assuming that we solve the differential equation, this lets us at least give us the knowing that it will be a balanced equation, because there's going to be, I totally forgot the 3 term. 3, because there will be a 3 multiple of the drive frequency being subtracted and balancing out the equation. And but this right away, this shows us that there is going to be there will be a term equal to 3 times the drive frequency that appears in our solution of this equation. And so when we're analyzing the motion, there's going to be a subtle change in the motion of the damp-driven pendulum, because it picks up this harmonic of 3 times the drive frequency. And a harmonic is just any n integer times the original frequency. And then we can see again, if we sub this whole new thing back into our equation, we're going to get even more harmonics showing up of the form n omega, because this whole process that we did here is just going to repeat itself, and we're going to come up with cos to another power, and we're going to break it down with identities, and we're going to get another n integer that's greater than 3 term built into our solution. And so we're going to get more and more harmonics piling up on each other, and that, I mean, their effects get smaller and smaller, but altogether they start to affect our solution. And so we can see how this starts to affect the motion of our graph, or the motion of our pendulum, slightly. Next, here. And so this might be slightly hard to see. Let me get this out of the way. This is graphed in Mathematica. Unfortunately, I do not know how to use Mathematica to graph these systems, but luckily there's a textbook that uses the exact same numerical values, and that's the John Taylor textbook. I'll put it in the references if you want to check it out. But here we can see how the damp-driven pendulum behaves now, and it's basically the same. This is still in units of drive frequency, so 1 period of drive frequency, 2 periods of drive frequency. And there's the initial transitory behavior before the eventual motion settles out to basic sinusoidal motion with frequency of the drive frequency. But if we magnify these crests and troughs a little bit, we can see that, I mean, the dotted line here is pure sinusoidal motion compared to the actual motion. So all these harmonics that are piling up because of our larger driving force are starting to affect the outcome of our solution. And so basically you can say that, in summary, for very small phis, and very small gammas, the behavior is going to be basically perfectly linear, just like a normal oscillator that we've been studying all the time. There's going to be some initial transitory effects here, but eventually it's just going to be drawn to the attractor, that is the natural driving frequency and amplitude of the driver. And then even as phi gets a little bit larger, or a little bit larger, and our drive force gets a little bit larger, we're still going to see basically the same thing with the initial transitory effect that's very small, but eventually the movement smooths out and continues on to infinity with the amplitude and frequency of the drive frequency, except because of all the harmonics we're picking up, there's going to be a slight modulation and variation, as shown here, in the waveform of our solution. But yeah, we'll see where that leads.